So the question is, find the eigenvalues and eigenvectors of matrix A. So here, to find the eigenvalues, we first need to find the characteristic equation. So the characteristic equation is A minus lambda I is equal to 0. Here, determinant of this matrix is equal to 0 is the characteristic equation, and finding the values of lambda are nothing but the eigenvalues of matrix A. So here, A minus lambda I matrix will be 8 minus lambda minus 6, 2, minus 6, 7 minus lambda. Here I is nothing but the identity matrix. 2 minus 4 and 3 minus lambda is equal to 0. Now, here we will use the trick, that is nothing but the determinant of this matrix is nothing but lambda cube minus sum of diagonal elements times lambda square plus sum of minors of diagonal times lambda minus determinant of A. So after calculating this, we will get lambda cube minus 18 lambda square plus 45 lambda plus 0 is equal to 0. Here determinant of A is 0. You can calculate. So we have to solve this equation. Taking lambda outside, we get lambda square minus 18 lambda plus 45 is equal to 0. After factorization, we need two factors of 45 such that their multiplication is 45 and addition is minus 18. So minus 15 and minus 3. So the factors are lambda times lambda minus 3 and lambda minus 15 is equal to 0. So our eigenvalues are nothing but 0, 3 and 15. Now we need to find the eigenvector corresponding to 0, 3 and 15. Let's see how to do that. So first case, for lambda is equal to 0. We need to solve this homogeneous equation. Lambda minus 0i times x is equal to 0. So this matrix will be 8 minus 6, 2. Here it is 0 times identity matrix. So the matrix will be as it is, minus 6, 7, minus 4, 2, minus 4 and 3 times x1, x2 and x3 is equal to 0, 0, 0. Now we can solve this using Cramer's rule. So solving by using Cramer's rule, we get x1 upon, we will eliminate this first row and first column, 7 minus 4, 3, which is equal to minus times x2 upon minus 6, minus 4, 2 and 3, which is equal to x3 upon minus 6, 7, 2, minus 4. So this implies x1 upon 5 minus x2 upon minus 10, x3 upon 10. So multiplying this with 5, we get x1 upon 1 is equal to x2 upon 2, which is equal to x3 upon 2. Hence, eigenvector corresponding to lambda is equal to 0 is x1 is equal to 1, 2 and 2. 1, 2 and 2. Second, for lambda is equal to 3. eigenvector is a minus 3ix is equal to 0. So here our vector reduces to 5. So here our matrix reduces to 5 minus 6, 2, minus 6, 4, minus 4, 2, minus 4, 0 times x1, x2, x3 is equal to 0, 0, 0. Solving by using Cramer's rule, x1 upon, here for x1 we will delete first row first column, for x2 first row second column, for x3 first row third column. x1 upon 4 minus 4 minus 4 0 is equal to minus x2 times minus 6 minus 4 2 0, which is equal to x3 times minus 6 4 2 minus 4. So this implies x1 upon minus 16, which is equal to minus x2 upon 8, which is equal to x3 upon 16. So again, multiplying this all by 8, we get x1 upon minus 2, x2 upon minus 1 and x3 upon 2. Hence, eigenvector corresponding to lambda is equal to 3 is x2 is equal to minus 2, minus 1, 2, column vector. Now, case third, for lambda is equal to 15. Our matrix is, our equation is a minus 15I times x is equal to 0. So this matrix will be minus 7, minus 6, 2, minus 6, minus 18, minus 4, 2, minus 4, minus 12 times x, that is x1, x2, x3 is equal to 0, 0, 0. Solving by using Cramer's rule, we get x1 upon minus 8, minus 4, minus 4, minus 12 is equal to minus x2 upon minus 6, minus 4, 2, minus 12, which is equal to x3 upon minus 6, minus 8, 2, minus 4. So this implies x1 upon 80 minus x2 upon 80, which is equal to x3 upon 40. So this implies x1 upon 2 is equal to x2 upon minus 2 is equal to x3 upon 1. So here eigenvector corresponding to lambda is equal to 15 is x3 is equal to 2 minus 2 and 1. Hence, our x1 is equal to 1, 2, 2. x2 is equal to 2 minus 1, 2 and x3, which is equal to 2 minus 2 and 1. So, we can write it as eigenvectors is nothing but our x1, x2 and x3, which is 1, 2, 2, then minus 2, minus 1, 2 and 2 minus 2, 1. See students, these eigenvectors and eigenvectors are for distinct eigenvalues. Here we have 3 distinct eigenvalues. For repeated eigenvalues, we will see in the next video.